Swayam Prabha. Digital India. Educated India.
Well, so we will continue with our discussion with the linear vector spaces. So, whatever we have done till now is that we defined a real vector space in n dimension, real as well as the complex space, and we have seen how will you define the normed linear space, the metric linear space, the inner product linear space, and what are the various properties these linear spaces will obey and satisfy, and what is the interrelation between the two, and given a vector how will you compute the norm metric or the inner product. And not only that, if we are moving from the discrete domain to the continuous domain, how the inner product, the metric and the norm will be defined for these continuous domain functions, whether it is a one dimensional function, or it is a two dimensional function, or it is a three dimensional function. Next, we are looking into some of the simplified examples, and in the first example we have seen how the given a vector, given two vectors, how will you define the metric between the two, the inner product between the two, and norm of each vector in discrete domain. The second example we have taken up is for a continuous two dimensional domain given by the functions f and g, and how the various quantities like inner product, norm and metric are defined for these cases. Now, we are looking into the second example where we are talking about the function f and g. So, in the last lecture we have looked into the norm of function f, and now we will be looking into how to compute the norm of g. This is given as norm of g square is nothing but integral over x, integral over y, x minus y square dx dy. So, it will be double integral x square minus 2 x y plus y square dx dy. So, it will be from 0 to 1 x square dx, 0 to 1 dy minus 2 x dx 0 to 1 y dy 0 to 1 plus dx 0 to 1 and y square dy from 0 to 1. So, if you carry out this integration, so this turns out to be 1 upon 3, this will be 1 minus 2, 1 upon 2, 1 upon 2 plus 1, 1 upon 3. This will be 1 upon 3 minus 1 upon 2 plus 1 upon 3. So, it will be 2 if we simplify this thing. So, this will be 2 minus 3 plus 2. So, 1 over 6. So, norm of g for this particular case is nothing but root over 1 upon 1 over root over 6. So, that is how we can develop the norm of f and norm of g. Next, we talk about the inner product between f and g. The inner product between f and g will be simply double integral 0 to 1 f multiplied by g dx dy, that is the definition. So, if you look into the expressions, you substitute the expression of g and x f. So, this will be x minus y 1 plus 2 x plus 3 y dx dy. So, just simplify this one. So, x plus 2 x square plus 3 x y minus 2 x y minus 3 y square dx dy. That is a simplification. Okay. So, this will be 2 x square plus x 3xy minus 2xy. So, this will be plus xy minus y minus 3 y square dx dy. So, 2 integral x square dx integral dy 0 to 1 plus 0 to 1 x dx dy 0 to 1. Third term will be integration x dx integration y dy. Fourth term will be integration 0 to 1 x multiplied by y dy 0 to 1. The last term will be 3 dx 0 to 1 y square dy 0 to 1. So, this will be 2 after carrying out the integration multiplied into 1 upon 3 into 1 plus 1 upon 2 multiplied by 1 plus 1 upon 2 minus 1 by 2 minus 3 into 1 into 1 upon 3. So, you will be getting 2 by 3 plus half plus 1 4 minus half minus 1. So, half will be cancelled out. So, it will be 12 3 into 4 4 to 8 plus 3 minus 12. So, it will be minus 1 by 12. So, that is the inner product between the two functions f and g. So, there is a difference between the two. In case of inner product of two vectors, that gives an angle, and in this case in case of functions, the inner product is computed by this method. Next, we talk about the metric. Metric between the functions f and g, square of that is defined as double integral 1 over x another over y f minus g whole square dx dy. So, it will be from 0 to 1 f is 1 plus 2 x plus 3 y minus g is x minus plus y dx dy. So, it will be 0 to 1 I simplify this 1 plus x plus 4 y square of that. So, this will be, just open up this square. If we open up this square, this becomes a square plus b square plus c square plus 2ab plus 2bc plus 2ca dx dy. So, your first one will be this one, second integral will be 0 to 1 x square dx dy from 0 to 1, third integral will be 16 dx 0 to 1 y square dy from 0 to 1, fourth integral will be 2 x dx 0 to 1 dy 0 to 1, fifth integral will be x dx 0 to 1 y dy 0 to 1, the last one will be 8 dx dy 0 to 1. So, if you compute all these integrals, this becomes 1 multiplied by 1 plus this will be 1/3 multiplied by 1 plus 16 into 1 into 1/3 plus 2 into half into 1 plus 8 into half plus 8 into 1 into half. So, this becomes 1 plus 1 upon 3 plus 16 upon 3 plus 1 plus 2, then this will be plus 4. So, 4 to 6, 6 1 7, 7 1 8, 8 plus 17 by 3. So, this will be 41 by 3. So, the inner product between the metric between f and g will be nothing but root over 41 upon 3. So, that is how the inner product of the metric inner product and norm of the continuous two dimensional functions can be computed. Next, we look into some more examples of this concept. The next example is for an n dimensional real space. Real space, we have three vectors x, y and z, and we have to show that first inner product between x and y will be less than equal to half mod of x square plus norm of y square. This is the first relation we have to show. The second relation we have to show that norm of x minus z square of that plus norm of y minus z square of that should be greater than equal to 2. Inner product between x minus z and inner product between y minus z. Okay. And these x, y, z are three general vectors having n number of real valued elements each. So, let us look into the solution. We start with the identity that sum of squares will be always greater than equal to 0. So, summation of x I minus y I will be square of that will be always greater than equal to 0. If x is equal and y are identical, then this will be equal to 0, otherwise it will be ever positive, because square is ever positive, sum of squares will be always positive, I is equal to 1 to n. So, just open up this square. If you open up this square, then what you will be getting is that this is nothing but x I square minus 2 x I y I plus y I square. So, will be greater than equal to 0. Next, you open up this summation. So, it will be summation x I square I is equal to 1 to n minus 2 summation I is equal to 1 to n x I y I plus summation I is equal to 1 to n y I square. Okay. So, by definition, if you look into the definition of summation of x I square, this is nothing but norm of x square of that. So, this will be nothing but norm of x square minus, and what will be this? If you look into the definition of the inner product, this will be nothing but the inner product between x and y, vectors x and y, and this will be nothing but norm of y square. So, therefore, we will be getting, if we rearrange this equation, we will be getting 2 of norm, the inner product between x and y should be less than equal to norm of x square of that plus norm of y square of that, and after that it follows the relationship that we are going to prove. That one will be nothing but inner product between x and y should be less than half of norm of x square plus norm of y square. So, that proves the relationship we wanted to prove. The next one will be the x norm of x minus z square plus norm of y minus z square should be greater than 2 times the inner product between x minus z and y minus z. In this case also we will be starting with the identity, but we will be starting with the in the next identity, that means summation of same identity will start with x I y I square should be greater than equal to 0, and we will subtract z I and we will add z I. So, this will be summation x I minus z I minus y I plus z I square. Again this is an identity. So, therefore, we rearrange this one x I minus z I square minus y I minus z I square, sorry, this will be square greater than equal to 0. Now, we open up this square. So, it will be given as summation I is equal to 1 to n x I minus z I square minus 2 summation x I minus z I y I minus z I plus summation y I minus z I square greater than equal to 0, 1 to infinity, 1 to n, 1 to n. Okay. So, what is this? By definition, summation x I z I whole square is nothing but the norm of the vector x minus z square of that, and this will be nothing but the inner product between the vectors x minus z and y minus z, and this will be nothing but the norm of vector y minus z square of that. So, now the whole equation is obtained. Now, this has to be rearranged and we will be getting our desired result. So, this will be norm of x minus z whole square plus norm of the vector y minus z square of that should be greater than to 2 times the inner product between the vector x minus z and y minus z. And that completes the proof of the next problem of the third problem that we have looked into. Let us go to the next problem. Let us look into some more problems, so that the method and the our intention is absolutely clear and the computation procedure will be clear. Now, let us look into the two vectors in R3 space. Consider the two vectors in R3 space. That means, each vector will be containing 3 elements. Let us say u1 3 1 2 transpose, and this notation is nothing but this same as 3 1 2, and u2 is 2 minus 3 5 transpose, and this is nothing but 2 minus 3 and 5. Now, what we have to do? We have to compute the metric between u1 and u2. Second part, norm of u1, norm of u2. Third part, the inner product between u1 and u2, and the last part is we have to check whether u1 and u2 are orthogonal or not. Orthogonal means they are perpendicular to each other or not. If they are orthogonal, that means the inner product between the two will be 90 degree. That means they are oriented at 90 degree to each other. Okay. Let us look into the solution to this problem. So, inner product between u1 and u2 is nothing but, if you look into the definition, it is under root summation x I, that means basically u I minus okay is under root summation u1 minus u2 square of that, I is equal to 1 to 3 in this particular case. So, it will be 3 minus 2 square of that plus 1 minus minus. So, plus 3 square of that plus 2 minus 5 square of that. So, it will be root over 1 plus 4, it is 16 plus minus 3 square. So, it will be 9, it will be root over 26. That is the inner product between u1 and u2. Next, we will compute the norm of u1 and norm of u2, part 2. So, in part 2, we will compute norm of u1 as root over square of each element and add them up. So, it will be 3 square plus 1 square plus 2 square. So, it will be root over 9 plus 1 plus 4, it will be root over 14 units. Similarly, you can compute the norm of u2, it will be 2 square plus minus 3 square plus 5 square. So, it will be 4 plus 9 plus 25. So, it will be nothing but root over 38. Next, we take up the third part of the problem. We have to compute the inner product between u1 and u2. So, if you look into the definition, so it will be summation over I is equal to 1 to 3. So, it will be u1 multiplied by u2 So, it will be 3 into 2 plus 1 into minus 3 plus 2 into 5. So, it will be 6 minus 3 plus 10. So, it will be 13. So, that is the inner product between u and u2. The last bit of this problem is that we have to check whether u1 and u2 are orthogonal to each other or not. They are not, simply because u1 and u2, inner product of u1 and u2 is not equal to 0. So, therefore, the conclusion is that u1 and u2 are not orthogonal to each other. Okay. So, that goes for the problem number 4. Then let us look into the next problem. The next problem says that we have two vectors, 3-dimensional vectors, 1 a and 2. So, they belong to n-dimensional space. The elements can be real, it may be complex or whatever. So, y will be minus 1, b and 3. Then we have to find out the relationship between a and b, so that for different cases, let us say case 1, x and y, each of them has norm 1. Okay. Second, x minus y has norm 1. Third case, x plus y has norm 1. Last one, x to y are orthogonal. In each of these cases, what is the relationship between a and b? That is the question. So, let us look into the solution. The first part, the x has norm 1, that means norm of x is equal to 1. So, therefore, it will be 1 square plus a square plus 2 square is equal to 1. So, a square is equal to minus 4. So, a is equal to plus minus 2y. Y has norm 1, that means minus 1 square plus b square plus 3 square is equal to 1. So, therefore, b square will be is equal to minus 9. So, b is equal to plus minus 3i. Now, in this case a is not, the relationship between a and b is that a is not equal to b. Now, let us look into the second part where x minus y has norm 1. So, norm of x minus y should be 1. That simply means 1 minus 1. So, square plus a minus b square plus 2 minus 3 square is equal to 1. So, you will be having 4 plus a minus b whole square plus 1 is equal to 1. So, a minus b is equal to plus minus 2i. So, that is the relationship between a minus b, and the third part is that x plus y has a norm 1. So, let us look into the vector x plus y. X plus y will be having the elements 0, a plus b, 2 plus 3, that is 5. So, norm of them is equal to 1. So, 0 square plus a plus b square plus 5 square is equal to 1. So, a plus b is equal to plus minus root over minus 24, it will be plus minus 2 root 6 times I. So, that is the relationship between a plus b, and the last part is that x and y are orthogonal. So, x and y are orthogonal. This relationship is indicated by this mathematical expression if the inner product between x and y should be equal to 0. So, let us compute what is the inner product between x and y. So, it will be inner product between x plus y, x and y should be summation of x I y I is equal to 1 to 3. So, it will be 1 into minus 1 plus a into b plus 2 into 3. So, it will be a b plus 5. So, this should be equal to 0 because x and y are orthogonal. Therefore, a b plus 5 must be equal to 0. So, a b is equal to minus 5. So, this is the relationship between a and b, so that you will be getting the various conditions satisfied given by this problem. Next, we just look into another problem that will be very interesting problem. The sixth problem, it is in the case of a continuous function in a continuous domain. It is a two-dimensional domain. So, we define a continuous function f as a function of x and y, where x and y are the two independent domain, coordinate system. So, this is given by ax minus y. Both x and y belong to the same domain, that means x varying between 0 and 1 and y is also varying between 0 and 1. Now, we have to find a such that norm of f is equal to 1. Okay. So, that is the question. Let us look into the solution. The solution is that norm of f square is equal to 1. So, if you look into the norm of f, this will be integral 0 to 1, this integral is over x, another integral over y. So, it will be double integral ax minus y square dx dy should be is equal to 1. Okay. So, we just carry out this integration. So, it will be 0 to 1, 0 to 1, open up this square, a square x square minus 2 a x y plus y square dx dy should be equal to 1. Then term wise we carry out the integration, a square x square dx dy, that is the first term. Second term will be, where a, in this case a is a scalar. We are going to find out the value of a. So, it will be x dx from 0 to 1, y dy from 0 to 1, third term will be plus dx 0 to 1, y square dy from 0 to 1 is equal to 1. So, a square into 1 upon 3 into 1 minus 2 a 1 upon 2 into 1 upon 2 plus 1 into 1 upon 3 is equal to 1. So, you will be getting a square by 3, 2 cancels out. So, a by 2 plus 1 upon 3 is equal to 1. We further simplify this equation and this becomes a square by 3 minus a by 2 is equal to 2 by 3. So, we will end up in a quadratic of a, and this will be simply 2a square minus 3a minus 4 is equal to 0, and this quadratic has to be solved. So, we will be getting the value minus b. So, it is plus 3 plus minus under root b square minus minus plus 4ac 32 divided by 2a, 2 into 2, that is 4. So, this a is equal to 3 plus minus root over 41 divided by 4. So, that should be the value of a, so that this function f, which is a function of dimension x and y. So, it is a 2-dimensional function that will be having a value, a norm 1. So, next we look into the next example. Again it is a problem of continuous function, and this function in this case is a 1-dimensional function. Let us say f x is equal to x square and g x is equal to x, where the domain of x is basically from 0 to 1. Now, in this problem we have a relationship, that is the metric between f and g, square of that, plus inner product between f and g plus norm of f square minus k norm of g square is equal to 0. If this algebraic relationship is valid, then find the value of k. So, again in this problem it is a 1-dimensional function. We have this algebraic relationship is satisfied, so that you evaluate the value of this scalar quantity k. So, the procedure remains almost same. We have to evaluate the metric between f and g, the inner product between f and g, the norm of f and norm of g, and substitute those values here and solve this one equation, one unknown problem. That will give you the value of k. Let us look into the solution. First, we talk about the metric between f and g. So, it will be integral 0 to 1 f minus g square dx. Since it is one dimensional problem, so it will be only one integration and this variable is dx. So, it will be 0 to 1 f minus g. So, x square minus x square of that dx. Just open up this square, it will be x to the power 4 minus 2x cube plus x square dx, and we carry out this integration x to the power 4 dx minus 2 x cube dx plus x square dx. So, this becomes 1 over 5 minus 2 over 4 plus 1 upon 3. So, just carry out this, simplify this one. The LCM is 60. So, it will be 12, 15 to 30 plus 20. So, it will be 32 minus 30 divided by 60. It will be 2 by 60 equal to 1 upon 30. Okay. That is the value of metric square of that. Then we will evaluate the inner product between f and g. That will be simply integral 0 to 1 f multiplied by g dx. So, it will be 0 to 1 f is x square, g is x. So, it will be x cube dx. So, it will be 1 upon 4. So, that is the value of inner product. Then we will find out the norm of f square of that. So, it will be 0 to 1 f square dx. So, it will be 0 to 1 x to the power 4 dx. This value is 1 upon 5. Next one is norm of g square of that. So, it will be 0 to 1 g square dx. So, it will be 0 to 1 x square dx. So, it will be 1 upon 3. Then we substitute all these quantities in the given expression. So, if you do that, you will be getting 1 by 30 minus plus inner product between f and g. So, that is 1 by 4. Then norm of plus norm of f square. So, it will be 1 upon 5 minus k times norm of g square. It will be minus k by 3 should be equal to 0. Okay. So, we substitute this k by 3 should be equal to 1 by 30 plus 1 by 4 plus 1 by 5. So, k should be equal to multiply both sides by 3, it will be 1 by 10 plus 3 by 4 plus 3 by 5. So, the LCM is 20, 10 in is 2, 5, 5 3 15 plus 5 3 3 3 9, 26 by 20. So, it will be 13 by 10. So, the value of k is nothing but 13 by 10 for this particular problem. So, this way we have seen how the inner product, metric and the norm of different vectors and functions can be calculated from various either in the discrete domain or for the continuous domain. And once we know the procedure to calculate them, we will be able to utilize them for solving different mathematical problems in chemical engineering applications. Next, we will look into another topic, the next topic that will be quite important, and again we will just go through the introductory stuff, that is the definition of onto, into and one-to-one function, and they will be quite critical in various chemical engineering applications. Now, onto, into and one-to-one function. Now, we consider there exist two sets. Let us consider two sets D and E sets. They are arbitrary sets. The x, the element x belongs to the D set, and the element y they belongs to the E set. Now, we define a function f in the D domain, and it assumes it operates on x. So, we define f in D set, and f operates on x. And it maps in y. So, we get, and after operation it maps in y. So, basically we are talking about something like y is equal to f of x. So, f and x are defined on D, and after operation the x is defined on D, and after operation y, when after f is operated on x, we get the value of y, and y is defined in the set E. So, therefore, we can say that for every x in D, there exists a corresponding y in E. So, it is a map. So, f is nothing but a map. So, when D is operated by f, it gives a map in the domain E. So, D is nothing but domain of x, okay, and what then next we define the R is nothing but the range of x. That means range of x means this gives a set. So, R gives a set comprising of maximum and minimum value of it is basically R is nothing but range of y. Okay. So, it gives a set comprising of maximum and minimum value of y in E for all values in D. So, that gives the range of y, and next we look into the relationship of this set R set and E set, because both are in y domain now. So, next we will have a relationship between R and E. Now, depending on this relationship between R and E, we define the function into or onto, and the definition goes like this: if R is equal to E, then f is onto function. If R is a subset of E, then f is into function. If for every x in D there exists a unique value of y in E, then f is called an one-to-one function. Okay. So, that is very important. That means, if y is equal to f x is equal to x square and both x and y they lie in the real domain from minus infinity to plus infinity, then we can see that for two values of x, y will be assuming the same value. That means, for x is equal to plus 1, y is equal to plus 1, for x is equal to minus 1, y is equal to plus 1. For x is equal to minus 5, y is equal to 25, for x is equal to plus 5, y is equal to 25. So, for values for different values of x in the in D, there does not exist a unique value of y in E. So, therefore, this function the f is not an one-to-one function. On the other hand, y is equal to 3x, if that is f, y is equal to f x is equal to 3x. For every value of x, there exists a unique value of y. So, in this case, f is a one-to-one function. Now, this concept will be absolutely clear if we look into some of the examples. Now, consider the function y is equal to f x is equal to x square. Okay, the first one we have I just talked about. For x is equal to plus minus 2, y is equal to 4. So, therefore, f is not an one-to-one function. Let us look into the second example. Y is equal to f x is equal to 1 over 1 plus x square. Now, in this case, let us say the domain of x, that is D, is minus infinity to plus infinity. That means, it belongs to the real line. X belongs to real line. So, domain of x is D is minus infinity to plus infinity. Now, for x is equal to plus infinity, y is equal to 0, and for x is equal to minus infinity also y equal to 0. But for x is equal to 0, y equal to 1. So, if you plot y as a function of x, so in one case it is minus infinity, in another case it is plus infinity, and for x is equal to 0, its value is 1, let us say this value is 1. So, the curve looks something like this. This will be having a maximum at x is equal to 0 and its value will be asymptotically goes down to 0 when x is approaching plus infinity to minus infinity. So, therefore, the range of y is nothing but from 0 to 1, and if we assume the E set such that E is comprising of minus infinity to plus infinity, then we can see that the range set R is nothing but a subset of E, because E is having minus infinity to plus infinity. On the other hand, range is only from 0 to 1. So, therefore, R set is a subset of E. So, therefore, in this particular case f is into function. If we define the E set as from 0 to 1, we have already seen if E set is from 0 to 1, then, and we have already seen the R set is also from 0 to 1. So, in that case R is equal to E. So, therefore, if for this definition of E set, f is an onto function. So, depending on the value of E set, the domain X, or basically everything depends on the domain D, range R, and the E set whatever we are talking about. So, based on these three values, based on the domain of X, R will be decided. Based on the domain of R, the relationship between R and E will be decided. Depending on that, the function definition f is defined. So, let us try to conclude this session, that we have already seen what, let us summarize whatever we have done till now. We have seen how the matrix, we have first defined the metric linear vector linear space, and we defined the metric linear space, the norm linear space, the inner product space, and we have found what are the various definitions these matrix spaces will be obeying and various axioms they will be obeying, and given for a discrete domain, for example, in vectors, or how these three quantities will be computed. For the continuous domain like functions, how these three quantities will be computed. In case of functions, if it is one dimensional space, it is two dimensional space, it is three dimensional space, how these three functions will be computed, and what are the physical significance of metric, norm, and the inner product, and how they are calculated for the functions in the continuous domain, for the vectors in the discrete domain. Then we moved over to the nature of functions, into functions, onto functions, and one-to-one functions, and we have seen that how we can define the range of the function for the. So, it is basically a map of the, we are talking about a function f, which is nothing but a map which takes up a value in x, that is in D domain, and maps into the y domain, that is in the E domain. And depending on the range of y and the domain space of E, whether it is a subset of E, whether it is equal or whether it is not a subset, depending on that we can define the function one-to-one, into, or onto. We look into some of the examples of onto function and into functions, and we will move over to the definition of completeness of space and a Cauchy sequence, which will be very important in chemical engineering applications. Thank you very much.